Welcome to Trig Identities, Round 2. We will take a look at the even and odd, sum and difference, cofunction, double angle, and half angle formulas today in this video. Before we begin, be sure that you have access to your unit circle, as we will use it for reference a lot. Also, be sure that you are writing down all of these different formulas/identities that we'll be learning today. There's a lot of them, and it's going to be helpful if you have easy reference to them. We'll start with a warm-up. Go ahead and pause and use your unit circle or your amazing memory to find these two values. Our two solutions are found here below. Number 1, the cosine of 5 pi over 3 is 1/2 the x value, and the sine of negative pi over 2 means moving in the negative direction, pi over 2, aka 90 degrees, which is really the same as positive 3 pi over 2. The sine is -1. Let's start by exploring what we mean by even and odd. Well, an even or odd function has to do with symmetry. If we take a look at this angle right here, which this picture is calling theta sub 0, we can call it anything. This is a positive angle because we're moving in the positive direction. Here, its coterminal side is right here, and we can see that the coordinates on the unit circle are clearly, of point P, are the cosine of theta and the sine of theta. Next, what if theta was negative? So we'd clearly be moving in the negative direction the same amount. And so we're down here, now in quadrant 3. Then we can see that point Q on the terminal side of negative theta is still cosine of negative theta and sine of negative theta because that is what we called that angle. Let's think about the relationship between P and Q. Clearly, they're symmetrical in some sort of way, right? They have symmetry across the x-axis if we were to flip it. So if we think about the cosine being the x value and the sine being the y value, what would the cosine of theta be? Well, it's clearly a negative value because we're moving left, and the sine would be a positive value since we're moving up. So this is some negative value, this is a positive value. Let's compare that to the values with point Q, the cosine of negative theta. Well, aren't we moving the same distance to the left, the same x distance here to the left on the x-axis? Yes. The sine is going to be a negative down here because we're moving down. So we can clearly see that the cosine of theta and the cosine of negative theta are the same thing because of that symmetry, whereas the sine of theta and the sine of negative theta are opposites. This leads us into our even and odd identities, our first identities in this video. We can see that when we had the cosine of negative theta, it still equaled the cosine of theta, as they were the same, x value. Whereas the sine of negative theta was opposite the sine of theta. They were opposite values. As we see here, cosine and secant are simply reciprocals of one another, and so therefore they're going to have the same identity. Cosecant and sine are also reciprocals of one another, so they are the same as well. Now, if we think about tangent, looking back on this, remember tangent is simply y over x or sine over cosine. We can think about P being the coordinate point A, B, or negative AB rather, because the cosine is negative and the sine is positive. Then we also know that down here, this cosine of negative theta was also negative a, but this was the opposite of b, as we were moving down below the same distance as we were moving up here to get to this y value. They're simply opposites of one another. If we think about the tangent of each one of these, the tangent of p, or rather the tangent of theta, I'm looking at point P, would be negative b over a, or b over negative a. Then we see that the tangent of negative theta is negative b over negative a. The negatives cancel out. So we can see that the tangent of our original is negative, whereas the tangent of the negative theta is positive. They are opposite outputs. Thus, looking here, the tangent of negative theta is the opposite of the tangent of theta. It falls along the same lines as sine. So if we had the cosine of pi over 3 and the cosine of negative pi over 3, they're the same thing. Whereas if we had the sine of pi over 3 and the sine of negative pi over 3, they're opposites of each other. Same with tangent. We can obviously always just look at our unit circle to confirm these, but it's showing that cosine and secant are even identities, where sine, cosecant, tangent, and cotangent are all odd identities. Our next identities are called the sum and difference identities, sometimes called the sum and difference formulas because they're basically formulas as well. While we can find the cosine, sine, and tangent, and also secant, cosecant, and cotangent of all of those important angles around the unit circle, what about angles that sort of get lost, like 15 degrees, or maybe 40 degrees, things like that? We are able to use the cosine, sine, and or tangent values of angles that we know, two of them, to add or subtract to get one of those other values like 15. And so we can see that in the cosine, sine, and tangent sum and difference identities, we have a plus or a minus here. That is just saying that if we have the cosine of alpha plus beta, two different angles, we're using the top sign plus. We look across here, we use the top sign of minus here. If we wanted to do the sine of alpha plus beta, we would use this plus here. And if we wanted to do, let's say, tan of alpha minus beta, we would use the bottom one for each. So the minus up here and the plus down here. So this is just a way to write 6 different identities in only 3 lines. Let's take a look at the first example. We want to find the exact value of the cosine of 15. Now we have to think about using our most popular angles on the unit circle to make 15 degrees. Well, our popular angles on the unit circle in quadrant 1 are 30, 45, and 60. Then we also have 0 and 90 degrees that are not on, they're both on the axes. How can we make 15 degrees out of those 3? Well, we could do 60 minus 45. That's one way to do it. We could also do 45 minus 30. So there's a couple different ways to get 15 degrees. I'm going to just use the first one that I picked, which was 60 degrees minus 45 degrees. If you picked the other one, it would still work. So we're going to do the cosine of 15. We know that that equals the cosine of 60 degrees minus 45 degrees. So my alpha will be 60 degrees and my beta will be 45 degrees. So this equals the cosine of 60 degrees minus 45 degrees. So every time I'm just going to write this out. Because it's minus, I'm going to use the bottom sign here, which is plus. So we'll have the cosine of 60 times the cosine of 45 plus the sine of 60 times the sine of 45. Here I took a snippet of the unit circle that we care about. Remember, pi over 3 is 60 degrees and pi over 4 is 45 degrees. All right, the cosine of 60 degrees is 1/2 and the cosine of 45 degrees is root 2 over 2. So we'll replace this with 1/2 times square root 2 over 2. Then we have plus the sine of 60 degrees is root 3 over 2, and the sine of 45 degrees is root 2 over 2. Then we'll clean up here using some algebra. So multiplying these first two fractions together, we'll multiply straight across the numerator, straight across the denominator as we do. Same thing with the second group of fractions. We'll get root 6 over 4. They have a common denominator of 4, so we'll have root 2 plus root 6 all over 4. No, we cannot add these two roots together as they are not like roots. They have different radicands, what's under them. So we cannot combine those to get root 8 or anything like that. That is not correct. This is our final answer, and this is the exact value of the cosine of 15 degrees. Next, we want to find the exact value of the sine of 19 pi over 12. That's a weird one. We do have to figure out how we can get to 19 pi over 12 using the common angles on the unit circle. Now, none of the angles on the unit circle are over 12, but all of those families are over 3, 4, and 6. And in that case, if we were to add any of them together, their common denominator would end up being 12. So let's think about some ways that we can get 19 pi over 12 by adding some of those common values on the unit circle, common angles rather. So just kind of thinking out loud a little bit here, I have the unit circle up and I want to think about ways to make 19 pi over 12. 19's pretty big, so I just took a look over here and got pi, 7 pi over 6, and 5 pi over 4 and put them all as fractions over 12. And so these are all, they seem a little bit too big, but maybe one of them we can we can add on to get to 19 pi over 12. So let's write down a couple more and see sort of where we stand for how to make 19 pi over 12. Over here I wrote down a few more. I ended up seeing that when we do 3 pi over 4 and 5 pi over 6, we'll get 9 pi over 12 and 10 pi over 12 respectively. So these two, it looks like, can add up to make 19 pi over 12. Now, are there other ways that we can get to 19 pi over 12, perhaps through addition or subtraction? Most likely, yes. But this is the first one that I found, so I'm going to go with it. So it looks like in order to get 19 pi over 12, we can add 3 pi over 4 and 5 pi over 6 together. Okay, so once again, I sort of zoomed in on the two angles that we want. You can make, with addition, obviously the order doesn't matter because addition is commutative, so we could have made either one our alpha and either one our beta. So again, a few different ways to do this. Now looking at the sign sum formula here, or identity, we're using the top sign here, SIGN, of plus, since it's a sum. So we're going to be using the plus in here. So I have 3 pi over 4 is my alpha value, and 5 pi over 6 is my beta. Let's replace it and figure out what we'll get. So I've rewritten the sign sum identity here, replacing alpha and beta with these two angles respectively. The sine of 3 pi over 4 is root 2 over 2, and the cosine of 5 pi over 6 is negative root 3 over 2. Next, the cosine of 3 pi over 4 is negative root 2 over 2, and the sine of 5 pi over 6 is 1/2. Now, simplifying this using some algebra, our first term will end up being negative root 6 over 4, and our second term is minus or plus a negative root 2 over 4 to give us negative root 6 minus root 2 all over 4. And this could be written like this if we wanted to make it look nicer and not have all those minus signs there, all over 4. So either one of these is acceptable. Yes, when we're doing sum and difference formulas, we do tend to get a lot of root 6s, root 2s, and all over 4s, just because of the nature of what all of these individual sine and cosine values are in the unit circle. In these next two examples, we will also be utilizing the sum and difference identities. We have theta is in quadrant 2, and the sine of theta is 5/13. Beta is a quadrant 3 angle with the tangent of beta is 2. We want to find the sine of alpha minus beta. So it looks like we do have a difference identity here for sine. So here is the sine sum and difference identities. The sine of alpha minus beta is sine of alpha times cosine of beta minus cosine alpha sine of beta. Well, we know the sine of alpha, it's 5/13. We don't know the cosine of beta, but we know the tangent of beta. We don't know the cosine of alpha, and we don't know the sine of beta. So we are only 1 for 4. That's not too good. However, with this information, we can actually find all these missing pieces by using a right triangle. Or rather, two right triangles, one for alpha and one for beta. So let's start with alpha. So since alpha is a quadrant 2 angle, I drew it going, so this will be like our x-axis, our y-axis here, and we're clearly extending past the unit circle, but we are on here's like the origin here. So the sine of alpha is 5/13. So here's alpha. Sine is opposite over hypotenuse, so we have 5 and 13. And then we can recognize that this is actually a super common Pythagorean triple, and the Pythagorean triple is 5, 12, 13. Now, if you didn't notice that, you could totally do the Pythagorean theorem and find that this missing side is 12. Now, we are in quadrant 2, so if you'd like to write negative 12, feel free. I like to keep all the values positive on my right triangle and then figure out what the trig function should be, positive or negative. So it looks like the cosine, we'll eventually need the cosine of alpha. The cosine of alpha would be negative 12/13, adjacent over hypotenuse, and since we're in quadrant 2, the cosine there is negative. So we know that the cosine of alpha is negative 12/13. So we know the cosine of alpha, we were given the sine of alpha already. So we have those two down. Next, we need to figure out stuff about beta. Beta is in quadrant 3, and we know that the tangent is 2/1. So when we're in quadrant 3, we'll be down here, and here's beta. Tangent is opposite over adjacent, and then we'll use the Pythagorean theorem to find the length of the hypotenuse. So we'll have 1 squared plus 2 squared equals our hypotenuse squared. So we'll have 5 equals the hypotenuse squared. So our hypotenuse equals the square root of 5. Now we are in quadrant 3, and therefore we're moving left and down to hit this coordinate point. Therefore the cosine and the sine are both negative, which is why the tangent is positive there. When we divide the two negatives, we'll get a positive tangent. So our cosine of beta and our sine of beta are actually both negative values. Let's identify them. The cosine of beta would be the adjacent, which is, in this case, it's negative 1 over root 5. So when we rationalize and multiply top and bottom by root 5, we'll get negative root 5 over 5. Then the sine of beta, which we also need to find, would be the opposite over the hypotenuse, and it's negative since we're in quadrant 3. Rationalizing by multiplying by root 5 over root 5, we'll get negative 2 root 5 over 5. So we have now found the sine of beta and the cosine of beta. Phew, now we can actually figure out what this all equals. So the sine of alpha we were given, and it's 5/13. The cosine of beta we found to be negative root 5 over 5. Then, since it's minus here, we're using the bottom, so it's minus. The cosine of alpha we found to be negative 12 over 13, multiplied by the sine of beta, and we found that the sine of beta is negative 2 root 5 over 5. Next, I'm going to multiply, so I'll get negative, and actually, let's take a look at what happens here. This 5 and this 5 cancel when we're multiplying, so we'll end up just having negative root 5 over 13. Then minus, we can see that the negative times the negative here will end up with a positive number here, but it's still minus that. And it doesn't look like we can actually cancel top to bottom at all, so we'll multiply straight across and we'll get 24 root 5 over 13 times 5 is 65. Phew! Now we need to get a common denominator. Well, we just saw that 13 times 5 is 65, so I guess I would have had that here either way. Maybe I shouldn't have canceled those 5s. So it looks like if we multiply the top and bottom by 5, we'll have what we would have gotten if we didn't cancel. Whoops. Minus 24 root 5 all over 65. When we continue to combine these and actually subtract them, we'll have negative 5 root 5 minus 24 root 5. So those are common terms or like terms. So we'll have negative 29 root 5 all over 65. And that is what the sine of our alpha minus beta is. In our next problem, we want to actually verify this identity right here. Now, we have not learned that this is an identity just yet. I sort of went in a different order than your book, but we're actually going to learn these cofunction identities in just a moment. But I want you to realize how these next identities that we're going to learn about, these cofunction identities, they actually come from the sum and difference identities. So let's take a look at this, and we basically want to prove that the cosine of pi over 2 minus theta equals the sine of theta. So here I brought what our cosine sum and difference identities are, and if we allow our alpha to be pi over 2 and our beta is theta, it's a little bit strange, we can actually rewrite this using the cosine of alpha minus beta, or the difference identity for cosine. So let's do that and rewrite the cosine of pi over 2 minus alpha here, or theta rather. So we'll have the cosine of our first angle, which is pi over 2. So the cosine of pi over 2. And let me actually write what we're doing. This is alpha right here, and this is beta. So the cosine of pi over 2 times the cosine of theta. Then we're doing the difference identity, so we're going to use the bottom one, which is a plus. So it's plus the sine of our alpha, which is pi over 2, times the sine of our beta, in this case, which is just theta. Now let's clean this up a little bit. The cosine of pi over 2 is 0. So since that's 0, it wipes out this whole term actually. So that term ends up going away. Plus the sine of pi over 2 is just 1 times the sine of theta. The first term goes away. We have one side of theta, which is sine of theta. So we have verified that the cosine of pi over 2 minus theta actually equals the sine of theta. This is actually one of the cofunction identities that we'll take a look at in just a moment, and they can all be verified in a similar way. These are the 6 cofunction identities, and basically it's just like shifting on the unit circle. So if we're shifting 90 degrees or pi over 2, we kind of get to what we want with another trig identity. These are not used as often, and I do not have a great example for really any of them, but just be sure that you have them written down, so in case we see them in the future, we can reference them and use them. So we saw that the cofunction identities came from these sum and difference identities. Another identity that also comes from those sum and difference identities, they're called the double angle identities. Now if we look and see what is there, it's literally what it's called, a double angle. It's 2 times an angle. Well, we can think about 2 times an angle, or 2 times theta, as theta plus theta. And therefore, these are all actually sum identities. This is the cosine of theta plus theta. This is the sine of theta plus theta. And this is the tangent of theta plus theta. It just happens to be sum identities where the 2 angles are the same, therefore doubled. I'm going to show you how we can actually prove this top one here. The cosine of 2 theta is really the cosine of theta plus theta. And therefore, we can use that cosine sum formula or identity, which says this right here. So the cosine of alpha plus beta would be the cosine of alpha times the cosine of beta minus the sine of alpha sine of beta. In this case, alpha and beta are both theta, since it's a double angle. So we'll have the cosine of theta times the cosine of theta minus the sine of theta times the sine of theta. Well, cosine of theta times itself is really cosine squared theta. And here, sine of theta times itself is sine squared of theta. So I have just proved this top one, that the cosine of 2 theta equals the cosine squared theta minus sine squared theta. Now, how did we get 2 other ways of writing this? How can we get from here to these other 2? We have to remember our most important identity, in my opinion, the Pythagorean identity, the first one, which says that cosine squared theta plus sine squared theta equals, drumroll, 1. Now we can actually replace these right here with what we can get from this Pythagorean identity. Remember that we rearranged each of these Pythagorean identities and solved for the other term. So the cosine squared of theta actually equals 1 minus the sine squared of theta. That's one that we found. And the other is that the sine squared of theta equals 1 minus the cosine squared of theta. So this is just all rearranging this Pythagorean identity right here. So let's actually replace cosine squared of theta with what it equals, 1 minus sine squared. So here in this next line, we can rewrite the cosine squared of theta as 1 minus sine squared theta. And then we still had a minus sine squared theta. So I simply replaced cosine squared theta with what it equals, which is 1 minus sine squared theta. And that comes from rearranging the Pythagorean identity. Combining like terms, we end up getting 1 minus 2 sine squared theta, which is an alternate way of writing cosine squared theta minus sine squared theta, which is what cosine of 2 theta was. So we got this one right here. So we've proved that one. We can prove this middle one in a similar way by replacing sine squared theta with 1 minus cosine squared theta. So that is why the cosine of 2 theta actually has 3 different ways that we can write it, because it works well with the Pythagorean identity of cosine squared plus sine squared equals 1. The other ones can be proved in a similar way, but they do not actually all use the Pythagorean identity. They simply can be proved and verified by using the sum identity for sine and tangent respectively here to get these two. So just be sure, even if you don't remember or know how to prove them, be sure that you have the double angle identities written down. Here is a problem that involves the double angle identities. We have, suppose point P lies at -3, 4, and it's on the terminal side of theta when theta is plotted in standard position. So it looks like point P is in quadrant 2 based on -x, +y. So it looks like the terminal side of theta is in quadrant 2. We want to now find the cosine of 2 theta and the sine of 2 theta and determine the quadrant in which the terminal side of that angle is in when it's plotted in standard position. So let's graph, or rather let's draw out the right triangle. Point P is -3, 4. So here's theta, and that means that our x value is 3, well, -3, and our y value is 4. So again, you can call this 3 negative if you'd like. We know that this is a common Pythagorean triple, 3, 4, 5, the most common one. Again, if you need to use the Pythagorean theorem to find 5, please do. So we have our right triangle here and our 3 side lengths. We now want to find the cosine of 2 times theta and the sine of 2 times theta. Now we need to use our double angle formulas in order to find this, but we're also going to need what the sine and cosine of just regular theta are. So let's just actually write those out first, the sine of theta and the cosine of theta. And again, we are in quadrant 2 here. So since we're in quadrant 2, our sine is going to be positive, but our cosine will be negative. So it looks like our sine is going to be 4/5 and our cosine -3/5. And we will use these to find the double angles. So here are the double angle identities right here for cosine of 2 theta and sine of 2 theta. Let's first find the cosine of 2 theta. So the cosine of 2 theta, we can use any one of these. I am simply going to use the top one here, which is cosine squared theta minus sine squared theta. So our cosine squared of theta is -3/5, or rather our cosine of theta is -3/5, and our sine of theta is 4/5. So we want to find the cosine of theta and then square it, and then minus our sine of theta and square it. So when we square -3/5, we'll get 9/25, and when we square 4/5, we'll get 16/25, and when we subtract, we'll get -7/25. So our cosine of 2 theta is -7/25. Then we can find the sine of 2 theta using that double angle identity, which is 2 sine theta cosine theta. Well, we know what each one of those is. We have to multiply them and then multiply by 2. So we'll have 2 times 4/5 times -3/5, which looks like it will equal, this is really 2 over 1. So we'll have 2 times 4, which is 8, times -3, which is -24, all over 5 times 5, which is 25. So we have found both the cosine and sine of our double angle. Now we have to determine the quadrant in which the terminal side of the angle 2 theta is in. Now if you think about an angle being in quadrant 2, the regular angle. If a regular angle is in quadrant 2, that means it's in between, between 90 degrees and 180 degrees. Depending on if it's closer to 90 or 180, if we double it, we'll either be in quadrants 3 or 4, just depending on which number we're doubling. Well, how do we know? Well, if we were in quadrant 3, our cosine and our sine of that doubled angle would both be negative, because that's what happens in quadrant 3. Whereas if our doubled angle was in quadrant 4, the cosine would be positive and the sine would be negative. We clearly have a situation here where both the cosine and sine of that doubled angle are both negative. Therefore, 2 theta is in quadrant 3. Here in this next problem, we want to verify an identity using all of the identities we've learned so far. So we have a double angle here of sine. We have what looks like a part of a Pythagorean identity because we have a 1 plus and something squared. So it looks like we can sort of mess with both sides here. So what I'm actually going to start to do is work with the left-hand side. We just learned today the formula for the sine of 2 theta is 2 sine theta cosine theta. It only has one formula, and it's our double angle formula for sine. Then on the right-hand side, I'm going to mess with this side a little bit too. In the numerator, I can't really do much. I could get it in terms of sine and cosine, so actually that is what I'll do. So I'll rewrite the numerator as 2, and then tangent can be rewritten as sine of theta over cosine of theta. And that 2, I'm just going to put it next to the sine, so it stays in the numerator there. All right, then all divided by, here we have 1 plus tangent squared. If you recall from our Pythagorean identities, this is actually equal to secant squared. So this equals secant squared of theta. Now on the right-hand side, I'm going to mess with this a little bit more. So we'll have 2 sine of theta over cosine of theta. Again, the 2 can go in either one of these positions. I'm just showing you both. Secant is the reciprocal of cosine. So this is really equal to 1 over cosine squared of theta. Now I haven't messed with the left-hand side, so all I'm going to do is just put quotes here to show that I'm bringing it down. Now still on the right-hand side, I have a complex fraction. So I want to kind of get rid of that complex fraction by multiplying by the reciprocal of the denominator. So we'll have 2 sine theta over cosine theta, not messing with the numerator at all. Then I'm going to multiply by the reciprocal of this down here, which is cosine squared theta over 1. When we multiply these together, I can cross cancel, and a cosine will cancel. So we'll have that goes to just 1, and this cosine squared, one of the cosines cancels, so it's just cosine. So look what we have. We have what we want. We have 2 sine theta cosine theta, and it does equal what we got on the right-hand side, which is 2 sine theta cosine theta. So we verified this identity by getting both sides of our equal sign to be the exact same thing. And the way we did that is we used our trig identities, the double angle identity for sine, as well as one of our Pythagorean identities, that 1 plus tangent squared equals secant squared. During this, we used another identity, which is this reciprocal identity. The reciprocal of secant is cosine, so the reciprocal of secant squared is cosine squared. Then we used an algebraic technique for simplifying a complex fraction. Our last group of identities today, or formulas rather, are the half-angle formulas. So we've had the double angle identities / formulas, and here we have the half-angles. This just means this is another way to find the trig functions for a specific angle on the unit circle. So we can use this in a similar way. Earlier we used the sum and difference identities to find the exact value of the cosine of 15 degrees. We can actually use the half-angle formulas to do the same thing. So these are alternate formulas for finding exactly what we need to find on the unit circle. Let's take a look at our first example. We want to specifically use a half-angle formula this time to once again find the exact value of the cosine of 15 degrees. So we have to figure out what did we take half of to get 15 degrees? 30 degrees. So we're going to use the cosine of 30 degrees over 2. So alpha will, I keep saying alpha, so theta will be 30 degrees. So we will have the cosine of 15 degrees. An alternate way of writing that is the cosine of 30 degrees over 2. So our theta value is 30 degrees. Now, this has a plus or minus in front of it. In fact, all of them do. It says we have to decide whether or not our cosine, sine, or tangent is positive or negative depending on the quadrant in which the terminal side of theta over 2 lies. So in this case, theta over 2 is 15 degrees. 15 degrees here is in quadrant 1. So that means the cosine and sine and tangent, all of them, would be positive because it's in quadrant 1. So we'll have the plus, so I don't need to write anything. So we'll have the square root of 1 plus the cosine of our theta, which is 30 degrees, all over 2. Using the unit circle, the cosine of 30 degrees, or the cosine of pi over 6, is root 3 over 2. So we'll have a giant square root 1 plus root 3 over 2 all over 2. Now, here's where the algebra comes in. So in our numerator of this complex fraction under a square root, we really have 2 over 2 plus root 3 over 2. So we really have 2 plus root 3 all over 2. And then we're dividing by 2, which really means multiplying by 1/2. So this is really times 1/2 here. So I did a couple things. I combined these two terms by getting a common denominator of 2. So we had 2 over 2 plus root 3 over 2. Then, instead of dividing by 2, I'm multiplying by 1/2. So we really have 2 plus root 3 all over 4. And then when we take the square root of the numerator and the denominator separately, we'll have the square root of 2 plus root 3, a root within a root, all over 2. Now earlier in this video, we found that the cosine of 15 degrees is really root 6 plus root 2 all over 4. And we actually found that by using a difference formula. We did the cosine of 15 degrees can be rewritten as the cosine of 60 degrees minus 45 degrees, and we ended up getting this as a solution. If you put both of these into your calculator, you'll see that they are the same. And if you'd like to give yourself a challenge, you can actually prove that they are the same. However, for the sake of this video, I am just showing you that there are two separate ways to find the exact value of the cosine of 15 degrees, much like there's multiple ways using all of these identities that we've learned today and formulas to find the trig functions for many, many different angles on the unit circle. In our final example for this video, we again will use the half angle formula. We are given some information about theta. We're told that theta is in between negative pi and 0. If you think about where negative pi is, it's the same place as pi because it's 180 degrees either way you go around the unit circle to 0. So this means that theta is either in quadrants 3 or 4. Now we're told that the cosine of theta is negative 3/5. We want to find the sine of theta over 2. So we are going to use our half angle formula for sine of theta over 2. And we can see that in this formula, we only need the information about the cosine of theta, which we have. However, we do need to decide, is it positive or negative? The choice of whether it's positive or negative depends on the quadrant in which the terminal side of theta over 2 lies. Well, we have information about theta. How can we figure out theta over 2? What we can do is use the information we've been given and get theta over 2 by dividing theta by 2. When we do that, we have to divide all 3 by 2, and we'll have that theta over 2 lies in between negative pi over 2 and 0. If we look at our unit circle, down here is negative pi over 2, and right here is 0. So that means that theta over 2 lies in quadrant 4. In quadrant 4, sine is negative. Therefore, we're going to use the negative sign in front when we find the sine of theta over 2. So we'll use our formula for the half angle of sine, and we'll have negative the square root of 1 minus the cosine of theta. The cosine of theta is negative 3/5, so it'll be 1 plus 3/5, and then divided by 2. Then let's simplify in here. So we'll have negative, then it's 5/5 plus 3/5, which is 8/5. Dividing by 2 means multiplying by 1/2. And when we simplify here, this 8 over 2 can be simplified to 4 over 1, so we'll have negative the square root of 4/5. Now when we take the square root of a fraction, we're taking the square root of the numerator and the square root of the denominator separately. So this is really negative 2 over root 5. When we rationalize and multiply both top and bottom by root 5, we'll get negative 2 root 5 over 5. And that is the sine of theta over 2. If you are reading this, if you are listening to this, it means that you have gotten through this entire video. So congratulations. I know it was a little bit longer than normal, but hopefully you have all of these different trig identities / formulas in your notes, and therefore we can do a lot of different things with them, and they're easily able to be referenced. Good job. Congratulations.